and inequalities after that. So this is 3.5. We do not cover 3.4 in this class. 3.5 rational functions. Can anyone give us an example of a rational function? The simplest possible one, we listed it when we looked at transformations, but we didn't work with it at all. And that was the simplest possible rational function. Exactly. It's a division of two polynomials. Very good. I divide these rational functions into three categories. We're not going to look at the third one.
Ever or just today?
Not in this class. However, I will show you an example if you'd like to. But we're going to focus on type 1 and type 2. So I'm going to give a few examples of type 1 and a few examples of type 2, and you'll tell me what is characteristic, what is typical in these. So the first one is 2x minus 4 over x plus 1. Of the same type 1, I'm going to give f of x equals x squared minus 1 over x minus 1, x plus 2. In type 2, I'm going to give x divided by x squared minus 4. And here's another, f of x equals x minus 1 over x to the 4th plus 4. And the third one, by request, when we finish what we, the plan for today, and then by request, I'll show you any type 3 you want. However, I will give you an example of type 3 so we know what it is. Here's an example of type 3. Okay, so let's go back and identify what is type 1? What do all these have in common from type 1? So then moving forward, we know type 1 requires blah, blah, blah. What would you say? So type 1 is degree n divided by degree n. Same degree over same degree. That's type 1. What about type 2? Degree n and degree greater than n. Larger degree in the denominator. That's type 2. What can you say about type 3? I just mentioned we have more than 3 types of rational functions. In this class, we cannot deal with more than these 3. And I'm excluding the third one only because, in the past I would present it, only because it was removed from pre-calculus. And then I said, well, if it's removed from pre-calculus, why would I present it in college algebra? So I thought that maybe this is beyond the scope of the course. But however, I will show you an example if you'd like. So, but we have to identify what it is and why is it different than the previous 2 types. Yes, yes. So, but specifically, the denominator has degree n, the numerator has degree exactly n plus 1. Not n plus 2, not n plus 3. Meaning, if the degree in the denominator is 1, the top must be 2. If the degree in the denominator is 5, the top must be degree 6. Okay, so let's start with the type 1. And in case you're wondering, again, which makes sense, you should, why are we even studying functions like these? These are difficult, complicated. Okay, here it is. Here's an example, and we'll come back to it when we finish. Here's an example. So we have here a drug is injected into a patient, and the concentration of the drug in the bloodstream is monitored. The drug's concentration C of T, in milligrams per liter after T hours is modeled by this. Can anyone identify the type of rational function? Is it type 1, type 2, type 3?
Type 1.
Correct. It's type 2 because the degree in the denominator is higher than the degree in the numerator. Very good. So here's another example. And here the function models the pH level. F of x, we're going to come back to both problems. Of the human mouth, x minutes after a person eats food containing sugar. Forget about the graph, we're going to graph them first when we get there. So just look at this. It's a rational function. What type is it? It is type 1, same degree over same degree. Degree 2 over degree 2, that's type 1. Degree 1 over degree 1, that's type 1. Degree 3 over degree 3, that's type 1. Higher degree in the denominator than the numerator, that's type 2. Higher degree in the numerator by exactly 1 unit higher, type 3. Okay? So that's why we want to understand these functions, what they do, what's special about them, and look at word problems. But we have to graph them. We have to understand how to graph them. Yes, please. Yes, of course. I'm going to post this. It's going to be there. So let's start by listing. So we're asked to graph. So we have to initially list the long list, and then once we fill out the chart, we fill up the chart, and we are done, as you know. So of course, domain, like always, this must be the first item. 2, x-intercepts. 3, y-intercept. Of course, n multiplicities if that's the case. We know that from the previous section on polynomials. The y-intercept. 4, something we have never discussed and we have never seen before. Vertical asymptotes. Vertical asymptotes and behavior. And behavior near the behavior of the function near vertical asymptotes. So vertical asymptotes and behavior near those vertical asymptotes. Item 5. Of course, max min. This is really annoying. It's a different angle. As we go into winter, it changes the angle. The sun. Okay, so next, item number 5. Horizontal asymptote, in parentheses or slant, not both, and behavior. They are together. 6, horizontal asymptote or slant, not both, and behavior. We know n behavior, we don't know asymptotes yet. 6, of course, max min. 7, symmetry, like before. 8, range. That's pretty much it. Okay, so let's start with the first one. F of x equals 2x minus 4 divided by x plus 1. Like always, this is a new topic. It will take me like forever. It will seem like forever till I explain and we go through it, and the next one will take 3 minutes or less. But the first one will take, it seems like it takes forever. Okay, of course, we will have to start with a table. We put all the information, we summarize everything like before in the table. And of course, I'm going to ask you what is the domain of this function. And what will you say?
All the numbers.
Never.
Negative infinity to infinity.
No. It's a rational function, right? It's not polynomial. We wish. This is not a friendly function. We talked about rational equations during the first week of classes, and we have to remember that something happens here. See? Very good. So negative infinity to negative 1. Negative 1 is not possible. The denominator cannot be 0. It's a rational function. Please remember. Please. Okay. So for now, as you know, the first time we go through this a similar example, we're going to check everything, and then everything will be presented in a table, and there is no need to go through the list anymore. Okay. So at this point, when I factor the numerator, I realize that x plus 1 does not go away with a factor of x plus 1 from the top. There is no factor at the top of x plus 1. Would you agree? Would you agree? We agree, right? There is no factor of x plus 1, so I can simplify x plus 1, correct? Is that clear? I'm saying that there is no factor of x plus 1 here that I could simplify with. Is that correct? True. Okay, so it's not. Because there is no such situation here, and the denominator does not go away, because I'll show you an example in when the denominator, or part of the denominator, will go away in a minute. After this example, we're going to do a look at one like that. We will immediately say that x equals -1 is a vertical asymptote. What does that mean? So let's explain the vertical asymptote now. This function, we know it's undefined at -1, which means there is a vertical line that this function will never cross. The vertical line is at x minus 1. It's x minus 1. The function cannot cross it. It's undefined here. But what does the function do near this, near the vertical asymptote? It does this. Or it does this. I don't know which one. We'll check in a minute. And on the other side, it does this, not both, or this, which means it goes to either infinity and negative infinity, or both infinities, or negative infinity, or this way. There are 4 possibilities. So once I establish that x equals -1 is a vertical asymptote, I can immediately write infinity left and right of that. So that's the vertical asymptote and behavior near the vertical asymptote. However, I do not know the signs. That's not a problem. I will use 2 numbers very close to -1, like -1.1 and -0.9. Notice that I do not put them in the table. I'm not going to use them to graph the function. I'm only going to use them to identify the signs. So if I plug -1.1 in here, the numerator is negative. Would you agree? If I plug in -1.1 in here, I hope you agree the denominator is negative. Would you agree? Just plug in. -1.1 minus 2 is a negative number. -1.1 plus 1 is a negative number. Would you agree? Yes? Okay. So then what is the sign of negative over negative? That's it. So the left-hand side of the vertical asymptote goes to positive infinity. Let's try -0.9. -0.9 minus 2 is still negative. But what about -0.9 plus 1? Very good. So what sign is negative over positive? That's it. So we established the signs of infinities. We established that x equals -1 is a vertical asymptote. We picked 2 numbers close, left and right, close to -1, and we just simulated that we plugged them in. We really don't have to. We are only looking for the sign. Do we understand this step? Good, let's move on. Now let's talk about the horizontal asymptote. Horizontal asymptote and end behavior. Okay, what does that mean? Well, it's the same situation that we had with polynomials. Even degree, this or this. Odd degree, this or this, depending on the leading coefficient, correct? Okay, but now these functions approach a line horizontally. They don't do this or this or this. No, they approach a line horizontally, and that is the horizontal asymptote. So because it's type 1, the horizontal asymptote is the leading coefficient divided by the leading coefficient. What is the leading coefficient of the numerator? What is the leading coefficient of the denominator? Very good. So y equals 2 over 1, which is 2, is the horizontal asymptote and behavior for all type 1 rational functions. 2, y equals 2 horizontal asymptote. So then this is done. Max min, we'll see if we need it. Range will, after the graph. Symmetry, there is no function that is symmetric. There will be symmetric if it only has a vertical asymptote at -1, but we'll write that down. So now let's focus on x-intercepts and the y-intercept, and we're done. Let's plug in 0. When we plug in 0, what do we get? Excellent. That's all I needed. When x is 0, y is -4. So that's the y-intercept. So now let's look at the x-intercepts. When is a fraction 0, right? So we have f of x equals 0. 2 times x minus 2 over x plus 1 equals 0, and 0 over 1. To refresh our memory, we've done this, I know it's a very long time ago. So after you cross multiply, you get that x minus 2 equals 0, or x equals 2. This is it. Let's try and make sense of this information and then put everything together in a graph. Let me know when you're ready. Any questions? Any questions? Okay. So on the left-hand side, we start from the left to the right, right? From approaching 2, going up to infinity. This is what I see here. From approaching 2, going up to infinity. On this side, from negative infinity, crossing the y-axis at 0, -4, crossing the x-axis at 2, 0, and approaching 2. One more time on this side, from negative infinity, crossing the y-axis at -4, 0, crossing the x-axis at 2, 0, and approaching 2. When we graph functions with asymptotes, we have to graph the asymptotes first. So let's give it a shot. And that's all it is to it. Okay, so first of all, -1. X equals -1 is the vertical asymptote, and 2 is the horizontal asymptote. A function can cross a horizontal asymptote. That is possible. But it will never cross what? The vertical one. It's not possible. It will never cross the vertical one. Okay, so now let's start by plotting the points. I only have 0, -4, and 2, 0. And basically that's all I need. Ready? So the table says from 2 approaching infinity. Fine. The table says from negative infinity, cross at 0, -4, cross at 2, 0, and approach 2. No problem. And this is the graph of the rational function 2, x minus 2 over x plus 1. With a graphing calculator, so you can still look at it because I did not prepare the software. Need a second. Okay, very good. So let's take a look. So in y equals, please be very careful. When you put in a rational function, you have to have parentheses around the numerator. So 2x minus 4. I didn't mean that. I meant this. 2x minus 4. Close the parenthesis and divide by x plus 1. The graphing calculator does not know to put in the horizontal asymptote, you have to put it in as a separate function. Let's say we use the zoom 6, the standard viewing window. So here's the function as expected from 2 approaching infinity, from negative infinity crossing at 0, -4, crossing at 2, 0, going to infinity, and this is going to 2, and that's the horizontal asymptote. Any questions about this function? Yes, please. Jordan?
You say the calculator won't give you the vertical asymptote?
The horizontal asymptote. You have to put it in as an extra function. And also, my apologies, I don't know how to make the software represent the vertical asymptote. But the horizontal asymptote, we can always put it in. But the vertical, I have no idea how to put it in the software. I have to do some research. But we don't need it. We know it's there. Very good. Any questions? Yes. Tim?
No.
Okay. Questions? Okay, let's take a look at the following. So let's say f of x equals x minus 1 over x minus 1, x plus 2, x minus 3. Let's start with the domain. Can anyone give us a domain?
Negative x. Oh, negative infinity.
To -2.
Very good. Negative infinity to -2. Very good. Very good. Awesome. So in other words, this function is undefined at -2, 1, and 3. Are you all with me? Is this clear why?
No, me explain.
I'm sorry?
Not really, ma'am. Can you explain?
Yes. The rational function is undefined when the denominator is 0. Is that okay, everyone? Yes? Okay. Very good. However, look what happens now. And by the way, what type is it? Before we establish. Cannot be.
Type 2.
It is type 2. The degree of the numerator is? The degree of the numerator is? The degree of the numerator is 2. The degree of the denominator is?
3.
Very good. Higher degree in the denominator is type 2. Very good. So it is type 2. I will simplify this particular factor. It doesn't mean that anything changes in the domain. It only means that x equals 1 is not a vertical asymptote, but a hole in the graph. It means that x minus 2, x equals -2, and x equals 3, since their factors stay in the simplified form, these are VAs. Guaranteed. And I can immediately write infinities. However, I don't have the sign of the infinities. But the simplified form is x divided by x plus 2, x minus 3. The two factors left over, x plus 2 and x minus 3, they have their role. They change into vertical asymptotes. Or not change, but they are vertical asymptotes. Let's determine the signs left and right. Let's say with -2.1 and -1.9, and let's say with 2.9 and 3.1. Let's do this together so we're all on the same page. So I'm using -2.1. -2.1, a negative number. -2.1, what do I get here? I just need the sign. Very good. And the -2.1, what do I get here? Very good, negative. It's -2.1 minus 3. So 3 negatives, what sign do I get? Very good. Negative sign. With -1.9, the numerator. I plug in negative 1.9. What is the sign? Perfect. So then I plug in negative 1.9 plus 2. What is the sign?
Negative.
Negative 1.9 plus 2. Very good. And with negative 1.9 minus 3, I see two negatives. What is the sign?
Positive.
Very good. Awesome. Positive indeed. When I divide two negative numbers, I get positive. 2.9. I plug in 2.9. What do I get? Sign. Just sign. Very good. I plug in 2.9. What do I get? Good. And I plug in 2.9. Very good. So what is the sign here? There is only one negative, right? Is that okay? Let's plug in 3.1, the top. 3.1 plus 2. 3.1 minus 3. Very good. So the right-hand side is positive. 3.1 minus 3. Which one is bigger?
Oh.
Okay? Good. Say it again. Okay, so now let's plug in 1. Because left and right, we do not have infinities. This is a hole in the graph. So 1, let's determine f of 1. F of 1. 1 at the top, 1 plus 2 is 3. 1 minus 3 is negative 2. So this is negative 1/6. Negative 1/6, negative 1/6.
Are the vertical asymptotes always the same? Like on the infinity side, if there's two, is the first one always the same?
No.
as the second one?
Very good question. No. No. Absolutely not. It all depends on the function, but very good question. Remember, with the asymptotes, there are 4 possibilities. 1, 2, 3, 4. They are not connected whatsoever. Very good. Good question. Now, what is the horizontal asymptote for all type 2? The denominator is much stronger and much bigger. The numerator is tiny. So imagine you divide a cake by 20 people. How much would you get? What if you divide it by 100 people? You have a, I don't know, 6-inch cake or pizza, and you want to divide it by 100 people. How much would you get? Almost nothing. So the horizontal asymptote for type 2 is always
Almost nothing.
0.
y equals 0. 0. Y equals 0 horizontal asymptote. I just want you to plug in 0 and we're done. And let's come up with a graph. So let's plug in 0. 0, 2, negative 3. 0 divided by negative 6. What do we get? 0 divided by negative 6. Very good. This is it. That's all we need. When we graph functions with asymptotes, we have to graph the asymptotes first. Ready? How many asymptotes are we going to graph? We're going to graph 3 asymptotes. However, this is an overkill, which is y equals 0. Why? Because it's already the x-axis. I don't need to graph it again. But let's say it's there. Then we have to graph negative 2, x equals negative 2. And then we have to graph 1, 2, 3, x equals 3. And then to make sure I don't forget, I would like to plot this point. 1 comma negative 1/6. It's very tiny. So I'm going to say it's here. 1 comma negative 1/6. Let's make sense of the table and then come up with a graph. Ready? From approaching the horizontal asymptote, which is 0, going down to negative infinity. That's this piece. Would you agree with the first piece? From 0 down to negative infinity. Agreed? Let's see what we have in the middle. From positive infinity, crossing at the origin, going through the open point, and going to negative infinity. In the middle. So from positive infinity, crossing at the origin, going to the open point, and going to negative infinity. on the last piece, from positive infinity to 0. Let's look at it one more time. So from 0 to negative infinity. On the other side, from positive infinity, crossing at the origin, going through the open point, going to negative infinity. The last piece, from positive infinity to 0. Ready? So, from 0 to negative infinity, here it is. From positive infinity, crossing at the origin, going through the point, the open point, and going to negative infinity. And on the last piece, from positive infinity to 0. This is it. Now we know how to graph rational functions. They're not easy. And this is type 2 because it has a horizontal asymptote to be, the horizontal asymptote is 0, y equals 0. They're not easy, they're not difficult, we just need to practice. Any questions? Any questions? I'm sorry? Every time a factor disappears, and the function, the original function is undefined at 1, but it disappears because I was able to simplify it with a factor from the numerator. This point, 1 comma, we don't know yet what, is a whole. So in order to determine these values, I plug in 1 here. 1, 1, 1. 1, this is 3, and this is negative 2. 1, 3, negative 2. So I get negative 1/6 on both sides. Is that better? Other questions? Yes, Tim.
On type 1,
Yes.
I lost myself with getting the asymptote.
The horizontal one?
But
Okay. So the
and
vertical.
on the
Did you put it in?
I missed it.
Okay. So you have to have a left parenthesis. So this is 2x minus 4. Close the parenthesis and divide by x plus 1. Close the parenthesis. And then you need a second function, which is 2. And you want to use standard for now. And here it's coming. And then the horizontal. Is that better?
That's simple.
Yeah, but you have to be careful to put parentheses. If you don't put parentheses, top and bottom. Okay, so let's also graph this with the graphing calculator if you'd like. The calculator will not be too honest in the sense that it will not really show that whole. So let's go to y equals, clear. You don't have to put the second function as y equals 0 because it's already the x-axis. There is no need for that. So the numerator, be very careful, parentheses, x minus 1, close the parenthesis and close another parenthesis, divided by, in parentheses, and parentheses again, x minus 1, close, parentheses again, x plus 2, and parentheses, and close again, and open another one, x minus 3, close the parenthesis, and close again for the denominator. So we can again use a standard 6, which is, okay, so it's coming from approaching 0 to negative infinity. It's coming from positive infinity, crossing at 0, 0. There is an open point here that it does not show, but we know it's there. And then the other side, which is from positive infinity to 0. Now, if you zoom in this area quite a lot, which I can do right now, I change the viewing window, let's say, between -2 and 2, and for y minimum between -1 and 1 with a scale of 0.5, then you will see it. I hope. Let's see. A little hole. It's obviously that it's not a vertical asymptote there. It's just a little hole. But if you use standard viewing window, you will not be able to see it. But we know it's there because the function is undefined at 1. And we know it's undefined at 1. I mean, we started from the beginning and by stating the domain. So what I would like to do next is, and of course we're going to review this on Monday. What I would like to do now, present the last section and then come back to more word problems and more rational functions. The last section I think you're going to like because it's just like a puzzle.
Great.
So this is 3.6, polynomial and rational inequalities. Last section before the test, and then we review. Okay, so for example, x, negative x plus 2, and x plus 3 less than or equal to 0. This is one example that I would like to look at. Here's another example. And here's the last one, and of course, more examples as you wish. Three examples. Okay, so can anyone tell us what is the first one? Is it a polynomial or a rational inequality?
Rational.
There is no ratio. It is a polynomial. Very good. What is its degree? Very good. Degree 3. X times x times x. Excellent. So the first one is a polynomial inequality. What about the second one? Yes, degree. So this was degree 3. Very good. And this is degree. Very good. Awesome. So it's also polynomial inequality. Both first two. What about the last one? Yes, awesome. Rational. Rational inequality. Let's start with polynomial ones. I recommend the following table in which we summarize everything. I think it's going to be easy to read. I accept other methods, of course. So we have this, I'm just copying it here one more time. So the table I highly recommend is this. X is the variable in the problem. So X right now does not represent anything else. It only represents the fact that that's the variable we're dealing with. We're dealing with X. And it can be anything. The next row is the first factor, X. The second row is the next factor. The last row here is the last factor, but there is also the whole thing, because that's what I'm interested in. I'm interested in this, not in each piece separately, but in order to determine the sign or study the sign basically of the bottom, which is the entire expression, I have to study each and every one of them. So can anyone tell us where is this 0?
What?
When x is? Of course, when x is 0. Where is this 0? When x is? 2. Awesome. Very good. Where is this 0? Excellent. So these are the only numbers I need in the table. You said -3, 0, and 2. I don't need anything else. So where do I put the 0 in the first row? Only under one number. Which number? Where is this 0? I have to put 0. Exactly. Very good. Where is this 0? One more time. Very good. Awesome. And again, where is this 0? Excellent. Now I need, for each of these 3 numbers, I need to know what happens to the product. What do you think happens to the product when either of these factors is 0? Of course. When any factor in a product is 0, the result will always be 0. Excellent. Okay. Now, based on polynomials, we know that all these are what type of functions? X, -x plus 2, and x plus 3. What functions are they? Excellent. Linear functions. Now, the first one looks like this, or looks like this?
X.
Right. So it goes from what sign? That's it. Perfect. Excellent. Now the second one. Does it look like this? Or does it look like this? Yes. It's coming from, it comes from 2. Last one. Does it look like this? Or does it look like this? I know it looks silly, but I like to do this in front of you.
Negative.
Excellent. Because it's a positive leading coefficient. Awesome. Great job. So now, on the first subinterval, yeah, it's. I thought it was easy to see, but it's not easy to see. Okay. On the first subinterval, I multiply two negatives. Outcome. Excellent. On the next subinterval, I have one negative. Very good. Awesome. On the next subinterval, I have only positives. Excellent. And on the last subinterval, I have one negative. Very good. Now, I look at this, and I'm asking you which sign, we only have two signs, which sign is less than or equal to 0? And you will say, negative. Is this product ever negative? Yes, here and here, which literally means here and here. So can anyone write the solution or tell us how to write the solution? X in the interval. -3, 0, union 2 to infinity. As I said, it's like a puzzle. If you prefer plugging in numbers, you can do that. That's fine too. That's what the book shows. I prefer this table. It's up to you. If you like it, use it. If you don't like it, use the other method. Very good. So let's look at number 2. Another polynomial. Good. So how do we solve this one? What do I have to do first? One thing I would like to mention. This table works only if this side is a product or a ratio, and this side is 0. Otherwise, you cannot use the table. So the left-hand side must be a product or a ratio of factors, and the right-hand side 0, or the other way around, it doesn't matter, but one side has to be a product or a ratio. So what do you recommend here next? Of course, thank you. That's all I want you to say. Excellent. Because the left-hand side is not a product yet, I can't use the table, but now I can. Great job. So this is an easier situation. This is the x is the variable in the problem. Then I have one factor of x, one factor of x minus 4, and the whole product at the end. How many x values will it give me to put in the table? And of course, you have to say 2 because there are only 2 factors. When there are 3 factors, you will say 3. When there are 4 factors, assuming that they are different, they're not the same. So what will you say? You're going to say 0 and 4. You're going to tell me to write 0 under 0 for x, and you're going to say 0 under 4 for x. And you're going to say 0 and 0. Would you agree so far?
Yes.
So this is just a piece of cake now, right now, because both of them look like this, right? Both of them have a positive leading coefficient. I don't have to plug in numbers. I don't have to calculate anything. It's negative to positive. Just put the signs in. And now, as you see, this is a product of 2 negative numbers. What will be the sign of the outcome? This is a product of a positive and a negative now. And this is a product of 2 positives. This symbol now tells me what to pick. And there is only 2, we only have 2 numbers. I'm sorry, I meant to say signs. We only have 2 signs. Which sign is greater than or equal to 0? Positive. Is this product ever positive? Of course it is. It's here and here. But I need to choose the x values corresponding to that. Those are the x values that make this product positive. If I pick a value like 1, the product will not be positive, will be negative. If I pick a number like 10, the product will be positive. So finally, in order to write the solution, I will say x in the interval, negative infinity to 0, because I have the equal symbol, I have to use a bracket, and then union 4 to infinity. That's the end of chapter 3, but I'd like to go to the rational inequality, and then go back to word problems from the previous section.